Hello and welcome back to Differential Equations, section 5.4, the eigen stuff. So we are going to use eigenvalue eigenvector pair, which you studied in linear algebra, to solve homogeneous differential equations. I mean, we're talking about systems of equations. So where do we start? We start with the idea that we have differential equations with constant coefficients, and these constant coefficients we are going to immediately assign the matrix indexes so that you guys can place this in the matrix right away. And then x2 prime is a21 x1 plus a22 x2 plus a23 x3 plus dot dot dot. And one more, x3 prime is equal to a31 x1 plus a32 x2 plus a33 x3 plus dot dot dot. So, and then dot dot dot. So these are all the things. Now I can create, as we have seen before, we can create the matrix of entries for this. Now we have the independent solutions for this. So the vector x of t will be constant c1 x1 plus, and this is a vector, c2 x2 plus c3 x3 plus dot dot dot, which is by the superposition. And what we are going to do is we are going to assign a vector that well, first what I'm going to do is I'm going to pull all of these. So this is the solution vector, and now we have matrix A times x. So I am combining everything in here, where this matrix A is going to be the matrix of A11, A12, A13, going on forever. So all of the entries.
That's not x prime. X prime.
Yes, x prime, thank you. A31, I really don't remember if I actually, you know how it erases sometimes, so I don't remember if I put that prime there or not. The stream will tell. All right, so we have the matrix A, which is multiplied by all of these x's. Now x is a column vector that contains x1, x2, x3. So those are x1, x2, x3, those are all functions. x1 of t, x2 of 3, x3 of t, x4 of t, and so on. And we give them this numerics rather than having them as x, y, z, w, because we have limited amount of letters in alphabet, and these systems can get as large as we need to describe a certain phenomena. So instead of using x, y, z, you know, for the functions in respect to t, we're using x1, x2, x3, and so on. But we get the same thing. So now the matrix X is the matrix of, it's a column vector actually, but it's still a matrix. It's a column vector that contains all of the derivatives. So x1 prime, x2 prime, x3 prime, and all of those are in x prime column vector. And then you have x1, x2, x3, x4 in the x vector. So this is the most concise way, we saw that last time, to write the system of equations. So you put all of the constant coefficients in the matrix A, and you have all of your functions that are unknown here as this x. So now that we have that, we can assume solutions, and we assume solutions of the exponential form. Why? Well, we know that when you solve characteristic equation, right, and when you do the basic separation of variables for the population model that we did on the first day, you get some kind of e to something. And then even if your r's are complex, you are getting sine and cosine values, but those were derived through actually having a complex values on e's, which actually produce sine and cosine values. So those of you that know that sine x is equal to e to the I x minus e to the minus ix over 2I, you see the complex numbers all over the place for this definition of sine in terms of the e. And when you solve the characteristic equation, in that characteristic equation, when you end up having complex numbers, you are used to putting in sine and cosine, but actually that is the simplified form. The original form is to actually use e's. So e's are in charge, right? You are assuming the solution of e, and then if the R equation, right, the characteristic equation, if that one gives you complex values, there is a mathematical manipulation that you can use with e's and complex numbers to get to sine and cosine. So technically, you were taught regurgitated, right, form of, you know, if you have the distinct solution, it is e. If you have a repeated solution, it is e and then times t. And then if you have the complex, it's cosine and sine. But the reality is they're all e's. And then you just have extra stuff if it's not just real numbers or repeated. So what am I going to do? I'm going to assume that the solutions xi are the some kind of a vector v times e to the lambda t. Now instead of using a, lowercase a, I'm using letter lambda, which is Greek letter. It's equivalent to L, right? It's lambda. And what we do is we are going to assign, this is so x prime of I is going to be now vector v, is now, you just copy that. And then you have the chain rule kick down lambda, so you have lambda vi e to the lambda t, and you can have any one of these. Now, what that does for you is once you plug that in the system up there, you obtain the formula which will allow you to compute these eigenvalues. So when I take all of these and I see the form they have, I have this one, right? So I'm going to plug this thing here, and I'm going to plug this thing there. And it's really clear from my diagram what goes where, right? So I'm going to do that again better. So I'm going to take this value and plug it for x, because that's what x is, and I'm going to take a purple value here. Now again, these are proofs, derivations and so on. So what I have on the left-hand side is lambda times the column vector v times e to the lambda t is equal to the matrix A times vi times e to the lambda t, right? Now, we know that exponential function never hits 0, right? It's above x-axis. And because it doesn't hit 0, that means that we can divide both sides by it, and you will get that the lambda vi is equal to a vi. And then what we are going to do is move lambda to, well, the form that we actually use is lambda av. We can drop these i's because it's known what it is. So we get this, and now subtract lambda on both sides. You get a v minus lambda v equals to 0. Now, you can't really subtract these guys because this is a matrix that could be a matrix, you know, 3 by 3 times some vector v, and then over here you have a constant. Lambda is a number, 7 or -5. So you can't subtract these because they don't have the same size. Yes?
You cancel out v1,
There is no division for vectors and matrices, so we can't. But what we can do is we can multiply this lambda by the matrix equivalent of 1, and that is the identity matrix. So if I write this way, now we get to a position where we can combine them, and now when you factor out the vector v, you get a minus lambda I times vector v to equal to 0, right? And
what did you do? You just added the I?
I didn't add the I multiplied by 1. Because this I will take on any dimension that it needs to in order for these two matrices to combine. So technically, look, if you have number 3, you can multiply number 3 by 1 and obtain and get 3 back, right? Because you multiplied by identity. Now, if I want to make this 3 into multi-dimensional 3, I will go 3 times the matrix 1, 0, 0, 1, and you will get 3, 0, 0, 3 back. So you see that I went from having a constant times 1, but this is a 1, this is identity 1 for 2 by 2, right? So the 2D space. So you can do it at 3D, 4D, you can do it at this point anyway, because you know that identity matrix will be one that has once in a diagonal forever. So what we did is we just fixed the issue, and we obtained this equation, and now we have this equation that computes stuff. So now we can finally define the eigenvalues and eigenvectors, and then we're just going to use that to solve systems. So definition: the number lambda is called an eigenvalue of the n by n matrix A, provided that, and we have the determinant of A minus lambda I is equal to 0. So we just seen that you have why is the need for this? First of all, vector v, we don't want that to be vector of zeros. So if you have two things that are multiplying into a 0, well, one is 0 or the other one is 0, or both are 0. But we cannot have v to be 0. So the other thing must be 0. And that's where we get the equation that gets us eigenvalues. And then an eigenvector, so the second part of this, an eigenvector associated with the eigenvalue, lambda is a non-zero, important, so it's non-zero vector v, such that AV is equal to lambda v, so that, and then we write the equation we had above, A minus lambda I times vector v is equal to 0. Yes, v is a column vector, yes. So now, I wish I didn't use red for this. I wish I used purple, because now we have the eigenvalue solution of the problem, which is what we're focusing. The stuff that I wrote now is actually linear algebra. Oh, actually, I can put the the highlighter box around this. So here is the eigenvalue solution. Eigenvalue solution of solutions, right? Multiple solutions, because these are systems of multiple equations. So this of x prime equals ax. And that will go dx dt is equal to ax. So this is the problem. I'll just put the arrow. And then x of t is equal to ve to the lambda t is a solution. And then you have, I'll just say plus superposition. Because you are going to have multiple lambdas and you will have multiple solutions here, but we'll get there. So I'm going to put this on a cloud. There we go. Your job is to find eigenvalues and eigenvectors, and then you just put the solution together. It goes like this. There are no combining equations and dealing with the second order and characteristic equations. None of that stuff. All right, so here is the first example. I'm going to pick also another example from the textbook. This is just very quick for us to solve. So we have a system. Now you have x1 and x2. You can, rename this when you start studying. You can rename it as x and y if you want to. So you will have x prime and then x and y, and then y prime and then x and y if you want to. We are going to create all of the matrices that we need. So we have the derivative matrix is equal to matrix A, 4, 2, 3, negative 1, times the matrix of solutions, which is the matrix X. Now, we discovered that the matrix A is 4, 2, 3, negative 1, and that's the one we need. So now, what we do is we run the formula that will calculate the eigenvalues. And we do that by computing the determinant of A minus lambda I. Now, matrix A is 4, 2, 3, negative 1 minus lambda times 1, 0, 0, 1. You can skip all of these steps, especially those of you who went through linear algebra and know what's going on. So now you have 4, 2, 3, negative 1 matrix minus the matrix lambda, 0, 0, lambda, which now when you combine them, you have 4 minus lambda, and then 2, and then 3, and then negative 1 minus lambda. And you have to find the determinant of that. So to find the determinant of this, you will do the standard thing. So you have 4 minus lambda times negative 1 minus lambda, and then minus 6, and all of that has to equal to 0. So you see that you're getting an equation in terms of lambda. Lambda would be unknown, it's a quadratic, and this will give you 2 lambdas, which is exactly what you need, because you do have 2 functions to figure out, so you should have 2 degrees of freedom, right? So now when you FOIL all of this, you get negative 4 minus 4 lambda plus lambda squared minus 6 equal to 0. No coughing, lambda squared minus 3 lambda minus 10 equals to 0. And this factors into lambda minus something, which is 5, and then lambda plus 2 equals 0. And there they are. We got our eigenvalues. So eigenvalues are lambda is 5 and lambda is -2. Now, these eigenvalues turn out to be your exponents of ease in a solution. So,
like e to the something. So e to the 5t.
And e to the -t. Yep.
Right. Okay. Yeah.
So now what we are going to do is we are going to find the eigenvectors that are associated to these eigenvalues. So the eigenvalue input is lambda is equal to 5, and we are supposed to find the eigenvectors that are associated with this. So now what you do is you place this into your eigenvalue matrix. So 4 minus lambda, so it's going to be 4 minus 5, 2, and then 3, and then -1 minus 5. And you multiply that by some values a and b to get 0, 0 on the other end.
Right, so you have to solve for a and b now.
Yes. So now what we do is we get 4 minus 5, that's a -1, and that's a 2, and that's a 3, and this is -6. Now, there is a checkpoint for this. Guys, these rows, so row number 1 and row number 2, must be scalar multiples of each other. If they're not scalar multiples of each other, you did something wrong. So you see that the first row times -3 gives you the second row. So you must, absolutely must, have these rows to be dependent, right? Dependent. And now you have you come up with the equation, right? You come up with the equation. When you do this multiplication, you will get -1 times a plus 2 times b to equal to 0. So this is -a plus 2b equal to 0. Now this equation is a creature that you can use to get your vector, because you know that the vector is of the form a and b. Pick a value for either a or b. I don't care. I don't care what you pick, and I don't care for which letter you pick that number. It's kind of standard to pick. So you have over here that a is equal to 2b, right? So, you know, I would like to pick b equals to 1, because b equals to 1. If I pick 1, I can pick 17. It's okay. But I'm going to pick 1 for b, and that creates a to be 2. And now that creates the eigenpair, which is lambda is 5, and the so lambda 1, which is the first eigenvalue we considered, is 5, and the first eigenvector associated with 5 is 2, 1. So that's what I have for my...
Is it oh, it's dependent on b, that's fine.
Yeah.
I was going to ask you one more.
Yes. Where did I get this equation? When I multiplied the first row, because both of the rows will give you the same thing. We can only consider the top row. So when I multiply, you know the matrix multiplication, right? So we pick a and b, put it up on top of 1 and 2, so -1 times a plus 2 times b equals to 0, which is the top 0 over here. So we just pick the first row. Second row is going to give you the same thing if you cancel. Just.
So now that you have b and lambda, you can put that into the fact that...
Yeah, but we need to find the other set first. Yeah. And then we're going to put everything together, yes. So now we are working on the lambda 2, which was -1? It was like a year ago. -2. So it was -2. You will replace that 4 lambdas in your matrix A. So the lambdas in the matrix A, so what was the matrix A? It was 4 minus lambda. So that's going to be 4 minus negative 2, and then 2, and then 3, and then negative 1 minus negative 2 times a and b equals 0, 0. Again, a and b is the unknown vector that you are looking for. So this is 6, 2, 3, and 1. Observe that if you multiply the second row by 2, you get the first row. So again, they must be dependent, which means they have to be constant multiples of each other. So I can pick second row now. It doesn't matter. If I pick second row, I have 3a plus 1b, which is just b, is equal to 0. And from there, b is equal to negative 3a. So now, if I pick 1 for b, then, sorry, if I pick 1 for a, b is going to be negative 3. So I have my second eigenpair, which is lambda 2, is equal to negative 2, and the associated eigenvector v2 is going to be 1, negative 3. And now we just put the solution together. We're done.
You can still use like 6 and 2, right?
But it will cancel. Because once you write this as 6a plus 2b equals 0, I hope you would divide it by 2 right away to make calculations easier.
Yeah.
So now solution. And you just put this solution together. The solution is the x vector is going to be equal to your vector v1, which was 2, 1. So 2, 1 times e to the 5t plus the second eigenvalue is, second eigenvector is 1 and negative 3 e to the negative 2t.
Why are we getting actual numbers instead of arbitrary constants?
And then times the constant. C1 and the C2, yes. Yes. So this would be C1, so 2C1 e to the 5t, and then C1 e to the 5t, and then all of that stuff. Good call, young Padawan. Now, if you want to write this solution, so this is the solution. We are done. If you want to see the exploded version of this, you will just write x1 is equal to 2c1 e to the 5t plus c2 e to the negative 2t, and x2, right, which is a function, maybe I should put of t.
Which is e to the 5t.
C1 e to the 5t minus 3 c2 e to the negative 2t. So that's the exploded version if you want to write them separately. But it's much more concise if you write them as a matrix. Now, I hope you guys see that it doesn't matter. It doesn't matter how large is the system, as long as you can compute quickly the determinant, right, which is a pain in the neck calculation for larger systems, right? Determinant for 3 by 3, you have to, right, solve. You have to break it up into 3 2 by 2s, and then solve all of that. So it's getting exponentially more annoying to compute these things, but it's really straightforward. I mean, once you get some of these things done. Now, let's take a look at one of the examples from homework regarding these guys. And then we are going to take a look at the complex version of this, which is also interesting. I mean, it's interesting to me. You live in your own world. So I'll give you maybe 2-3 minutes to try on your own. x1 prime, this is problem number 8 in a textbook. x1 prime is equal to x1 minus 5x2. And then x2 prime is equal to x1 minus x2.
plus or minus.
Then what?
Yeah. And we operate in show.
That's what he said. Do we have to use sine and cosine for this?
I hope I copied this right. What do you mean sine and cosine? So 1 negative 5 and 1 negative 1, right?
Right.
Did it work out?
Lambda squared.
Oh, you're not doing it
You get
because...
imaginary values for lambda.
No, I don't want imaginary values for lambda. Alright, so we have to pick a different problem. No, I'm serious. Because I didn't teach the complex yet.
While we're there, lambda squared.
No, look. Look, it's gone. No, I'm Nick.
Well, let me ask
Let's...
you want us to teach us how to deal with imaginary numbers?
Yeah, but no, not at this point. I need to first you to do one problem. Hi.
If you just put that problem back, that you change in the first equation, the negative 5x squared to positive, let's say,
I can just pick a different problem.
you know what, I wrote all this?
Why you?
Now I just wasted paper space. Thanks.
You're welcome.
Alright, well, just...
I can't. I have a pen.
Oh, you have pen? Awesome.
Dude, when I was in Hornberg's class, if we didn't have a pen, we weren't taking the test.
This is the difference between taking a test and writing calculus.
No, Hornberg made us have a pen for the test.
All right, so let's say you know some of these concepts, so let's go. I have x prime is equal to matrix A 4, 1, 6, negative 1 times x. That's another vector right there. So we have...
This is the same one.
Yeah.
what do you mean the same one?
Well, it's a little different.
I mean, I'm getting the same polynomial for here on top. But once you do the lambdas,
Yeah, 4 minus lambda, and then times negative 1 minus
you
lambda.
do the cross fishing.
Determinant.
Yeah, you do the cross fishing.
Cross fishing. Oh my god.
It's cross fishing. It's a fishing, not a fishing. Fishing.
Cross fishy, like this? This is
Yeah.
a cross fishy. Oh,
Cross fishing.
cross fishy. Oh my god.
They're gonna be teaching that.
Is a cross fishy now?
Yeah.
What number?
Well, apparently we can't do this one either.
I mean, we can.
Is it complex or no?
No.
It's not complex?
Why are you freaking?
Okay.
Looks like it.
The pain. All right. So we have 4 minus lambda, 1, 6, negative 1 minus lambda. Oh, this is the same as the previous one.
Yeah. You're gonna get the same characteristic polynomial.
Oh, yeah. You need a vector.
Yeah, but you're not going to get the same Eigen Vectors.
So we are getting a vector.
But it's going, yeah, it's going to be different vectors. So what am I getting? I'm getting lambda squared. What is the polynomial? Lambda squared
Yeah, that's what we got.
minus
Minus 10.
3 lambda minus 10 equals to 0. And we are going to have a same lambdas, which is 5 and negative 2. Ah, great.
Negative 5.
It's our book ran out of problems. So V1, so to find first eigenvector, we use 5. So that's negative 1, 1, and then 6, negative 6 times AB equals 0, 0. So now you have negative A plus B equals to 0. So A equals B, and clearly 1, 1 works, right? So that's the first one. The second one is negative 2. So for negative 2, I have 6, 1, 6, 1, and then 1 and wait, what's wrong over here? What's my eigenvalue? Negative 2.
You did the second one already?
Yeah.
Okay.
So negative 2, that's a 6, 1, and then a negative 2, it's going to give me 1. You can't give me 1. I can't compute. Negative 2. Oh, it's a 6 over here. There we go. No, I wrote the wrong value. There we go. Equals to... I know. There we go. And we just use the first one, so 6a plus b equals to 0, from where b is negative 6a. So we'll pick a to be 1, and then b must be negative 6 to satisfy this equation.
Yeah, you want. We have some lost ones in the back.
Is everyone okay?
And then you can skip the steps.
And
Went to the you did the identity, multiplied the
what identity?
1, negative 6, and negative 6. Right?
You multiply a to negative 1 and b
No,
to
I
1.
know that. Okay.
Yeah. To get this equation here, which just disappeared. So a is equal to b. You pick either a or b, and then the second one has to be from the equation. So now I have c1 1 1 e to the 5t plus c2 1 negative 6 e to the no-coffee negative 2t. And there it is. You get 3 by 3 matrix, just more annoying to calculate eigenvalues. You get 3 eigenvalues, you get 3 eigenvectors, you get 3 of these parts of the string. And you can have, 10 by 10 matrix, that's 10 lambdas, 10 vectors. Yes? Which one?
Where you put equal 0, 0 vector over there.
Yeah, it's a homogeneous system. Because these are dependent. They are dependent. All right, so now we are going to deal with the complex lambdas.
Can we just do the problem that we were supposed to do, but like didn't do?
Sure,
Number 8,
eventually.
because we're already like 3/4 of the way done.
Yeah, we'll come back here. All right, so complex lambdas. You can deal with complex lambdas the same way as we dealt with real lambdas, but then your answers will be in terms of ease, and then those complex numbers will make their way into exponents of ease, and you get the whole mess. And then you would have to figure out how to go from that form back into sine and cosine form, which is the real form, and then you can do the rest of the math, that whatever you have to do. So there is a faster method, right, than working with ease. So we are going to start the problem exactly the same way and use exactly the same way to obtain lambdas, and then instead of using and the vectors, right, and then instead of using ease, we are going to figure out the nicer way to deal with the solution set. So let's start with x prime 1 is 4x1 minus 3x2, and the x2 prime is 3x plus 1 plus 4x2. So matrix A is immediately 4, negative 3, 3, and 4. And if you are, so now we're looking for lambdas, so you have to find the determinant of 4 minus lambda, negative 3, 3, and then 4 minus lambda. Determinant is 4 minus lambda squared plus 9, and that needs to equal to 0. So now when you square this, here you get 16 minus 8 lambda plus lambda squared plus 9 equal to 0. And you get the lambda squared minus 8 lambda plus 25 is equal to 0. So this is what you have. And now what you're going to do is solve this, right? You can use quadratic, so negative b, so it's going to be 8 plus minus square root of 8 squared is 64 minus 4 times the 100 divided by 2, which is 8 plus minus, and this is negative 36, so it's 6i divided by 2, and what we get is 4 plus minus 3i. So that's the little bit of pre-calculus there. We have two lambdas. Lambda 1 is 4 plus 3i, and lambda 2 is 4 minus 3i for our eigenvalues. So now we want to find eigenvectors. We put this in our eigenvector machine, right? So we have, what was the 4 minus lambda? So that's negative 3i, because 4's cancel, and then negative 3, and then 3, and then 3i times ab is equal to 0, 0. These guys are linearly dependent, as you can see. Multiplying by negative 3i on the bottom, you are going to get the same values. 4 minus 4, 0, and then plus 3, yeah. Oh, there's a minus over here, I missed. Yeah. I'm not going to use the second row, so even if you... no, that doesn't matter. No. It's a minus.
Entry 2, 2 is supposed to be positive.
What happened?
Entry 2, 2 is supposed to be positive.
Why?
This is 4 minus lambda 2.
4. I'm doing lambda 1 now.
Isn't wait, so what's the first?
What is 4 minus 4 plus 3i? 4 minus 4 minus 3i. 4 minus 4 is 0 minus 3i, and negative 3i. So just walk away, all right? Or should I go to the next level? Back off. Oh, now you want E, right? Well, you ain't gonna get it. So we have negative 3ia minus 3b equals to 0 when you do multiplication. Divide by negative 3. We have ia minus b, no, plus b equals to 0. And from here, b is equal to negative ia. So your vector is going to have, if you pick 1 for a, it's going to have negative I for b. Good. So now vector v2 is going to have 3i, negative 3, 3, and then 3i, right? You have 4 minus 3i. So these guys cancel, minus and minus gives you plus, so both are this. There we go. Yes. Yes, lambda 1 for lambda, and that's for second vector, lambda 2 for lambda. You plug in, look, you have this equation. So your lambdas will go to the two locations when lambdas are. So you put lambda 1 in both locations, and then solve for vector v1, eigenvector v1, and then you circle the whole procedure again for lambda 2, put lambda 2 in both locations, calculate as the second one, yep. So what we have over here, times AB, which is the eigenvector we're looking for, 0, 0. So now you have 3i a minus 3b equals to 0. Divide by 3, we have ia minus b equals to 0. B is ia. So if a is 1, b is I. So I have v1 and I have v2. So those are my vectors. You should put these little arrows on top. All right, great. So what do we have as the solution? Right. How does this work now? We have lambda 1, which is given as, I forgot, 4 plus 3i. And we have associated vector 1 negative I. And we have lambda 2 no coughing is equal to 4 minus 3i, and then 1i as a vector. Now, you can go and you can say C1 vector 1 negative I e to the 4 plus 3i times t, and and get that, but that's not the form that we like or respect, right? So can we actually just transform this immediately into sines and cosines and have the real answer? And the answer is yes. Right? So, but it's trickier, so you have to pay attention. So start from, first of all, we know that when you have e to the 4 plus 3i, e to the 4t is the real part. So that's going to survive. And then the 3i is the one that makes sine and cosine of 3t, right? So we know that from our previous life, right, in chapter 2. So what I can do is I can write that x of t is equal to 1 and I, which is the eigenvalue that is associated with e 4 minus 3i times t. Do what? Oh, we're going to put that at the end. I'm just going to write this out. So 1 and I of e to the 4t, and then we have our good old cosine 3t minus I sine 3t. Right? So that was that. And if you are to multiply these i's into everything, so we are going to have that this vector of solutions t is going to be e to the, I said e to the 4t, and now we have the 2, right? You multiply by 1, you get cosine 3t minus I sine 3t, and then the second one is when you multiply I, you get I cosine 3t, and then I times I is I squared is -1, and this negative makes it a positive sine 3t. And that's just the first eigenvalue, and so this is for the first eigenpair.
Question.
Yes?
The vector 1, is that the negative I you went with, or are you doing the first one?
This is, all of these are i's. This is negative I here, I don't know which one you're referring to.
The one next to it, by the e to the 4t?
This one? It's positive I.
Positive, yeah.
Because it's positive.
And why?
Oh, this was the second.
That's why
That's fine.
it's the same thing?
Yeah, but well, I use the minus and I use this. I use the appropriate ones. You see, the other one is negative I and it's plus.
Plus 3.
But I use the minus. You see the minus, right?
Yeah.
Good.
So why is it a minus I sign?
That's the form. Hmm? Cosine 3t.
Yeah, I get that, but why is it a minus?
Minus sine 3t. Minus I sine 3t.
Do what?
I? That negative I.
Yeah. I mean,
This one?
yeah.
It's a solution form.
Yeah, but where'd it come from? Because we see a positive I.
You just flip them, that's what I was just saying. Is that
You
what
see a positive I. When I distribute, it changes. So 1 times this and 1 times that is the first. We're not done with the solution. We're not even close to being done with the solution. So let's do the second solution. Just give me a second, okay? So now we have the second part of the solution, which is going to be 1 negative I with the e of 4 plus 3i over here, which is 1 negative I going from e to the 4t, and then so we have the same thing for the second one.
So when it be I cosine?
Do what?
Would it be I cosine 3t plus sine 3t?
There's a t over here. So now we have the same part as up there, which is a cosine 3t minus I sine 3t. There we go. And now we have the, that's good, that's good, that's good. So now we have the solution here for the x of t, which is equal to e to the 4t. And then when you multiply here, you get the cosine 3t minus I sine 3t divided by negative I. So that's negative I cosine 3t. And then negative I times negative I is positive I. So this is a negative sine 3t here. Which is, yep, I got it. So the positive cosine, there's an s here that disappeared, and then sine 3t, yes.
You said divide, did you mean multiply, or is there...
Multiply, yeah, if I said divide, sorry. So, yeah, we're multiplying with each row with this. So now, so this is the second one.
So I get where you're getting that, where you're getting 2.
So,
Just distributing that negative I and that 1
yep,
over 2. But where do you get the, like, if you just look at the second one, right? Where it says e to the 4t cosine 3t minus I sine 3t. Where's the negative I? Like, where did you get that form to make that? That's what I want.
this is the form for the complex solutions. We just use the basic, just single cosine when you compare them together. You can combine it into a single solution. Right now, we are going to ignore all of the complex complex parts and just pick the real parts out of everything and put the solution for the entire problem together. So that part doesn't even play the role in our solution at the end. So now, I lost it, there it is. So your x1 solution in terms of t, which comes from here, is going to be e to the 4t, and then from this parenthesis you are keeping cosine 3t and you are keeping sine 3t. The others are imaginary and you drop them. And you have the x2t, it's not going to fit here, x2 of t, which is e to the 4t, and then again you are getting, so let me put end, cosine 3t, and then you have negative sine 3t. Oh, they have to be reversed. Why are they reversed? Sine 3t. My calculation differs than the textbook.
You switched them. Your x1 is supposed to be x2 and your x2 is supposed to be x1.
Thank you. So we have the two solutions, and once we have the two solutions, we just put them together with the constant c1 and c2. So the x of t, which is the solution for everything, is c1 x1 plus c2 x2, right? And these are actually also vectors because of the column vectors on the other side. So now, the overall solution that we are looking for, x of t, is going to be c1, and then you have e to the 4t. Actually, no, e to the 4t can be kicked outside, because that's everything. And then now you have your c1, cosine 3t sine 3t, plus c2, negative sine 3t cosine 3t, and there we go. To what?
C2.
It's right here.
Yeah. Sorry, your x2. I'm still a little bit lost. Well, yeah, you're supposed to switch them, but, or I suppose your the x2 you have written up there, which is supposed to be x1. You said we're supposed to drop the i's, so shouldn't that be?
This term has I, and this term has I.
Right. So.
Sine's on the bottom.
Yeah, sine's
Oh.
on the bottom, cosine's on the top.
Haven't seen anything. Cosine 3t, negative sine 3t. Yeah, that makes everything wrong. No coffee. Let's do one more problem with the complex, since this one went stellar, as you can see. Yes.
Maybe number 8. I don't understand how you got the form of the cosine minus 1. Where is the minus 5?
It's the form of the solution for the complex eigenvalues. Did I define it anywhere? No, but let me find it. Page 374 in a textbook. So I'm just going to point the arrow into this thingy. Let's make it purple. Page 374. and it is equation between 20 and 21. It leads into 21. So it is actually, so I'll write 20 plus 21 references, and once you go to page 374, it will be there. They don't even box it or anything. They're right here. So that's equation 20. That's equation 21. The actual form is in between, not labeled at all. All right. Let's do the homework problem. Problem number 8, right, was the issue last time, right? So you can recycle your paper. Prime is equal to x1 minus 5x2, and x2 prime is equal to x1 minus x2. All right. So, matrix of coefficients, 1, negative 5, 1, and negative 1. And I'm not used to it. I'm not. And then we have take away lambdas. So we have 1 minus lambda, and then negative 5, and then 1, and then negative 1 minus lambda. Determinant of that, so that's 1 minus lambda times negative 1 minus lambda plus 5 equal to 0. So this is negative 1 plus lambda minus lambda plus lambda squared plus 5 equal to, I'll put 0 there, put 0 somewhere else. So lambda squared, these die, plus 4 equal to 0. And what we get is the lambda is equal to plus minus 2i. Is that what you have? Yeah. Now this eliminates the e part. There will be no e. The whole solution will be in terms of just sines and cosines. There will be no times e.
Is that because we don't have like 4 plus?
There is no real part on the complex number. So your real part for e lambda t is actually e0t for the part, which is 1. So we don't have it. Yeah.
So e to the lambda t was just like e to the 0?
Yeah, because there is no
Like
real part.
minus 4, we had 4.
Yeah. Earlier we had lambda equals 4 plus minus 3i, so you had e to the 4t, and then the 3 was working in sines and cosine. This part is now, this 4 is now 0, so e to the 0 is 1. All right. So we have a V1. V1 is going to have 1 minus 2i, negative 5, 1, negative 1 minus 2i. So this is when we plug in this thing. And we are multiplying this by AB. Get 0, 0. So we have 1 minus 2i times A minus 5b equals to 0. And this is where 5b is equal to 1 minus 2i times A, and therefore b is equal to 1 minus 2i over 5 times A. So if you choose your A to be 1, then B is 1 minus 2i over 5. What happened? Okay. Lauren had an awesome idea, which I didn't even look. I am erasing everything using the other side of my pen. So if we use the second equation, we have a, and then if you factor out minus sign, you have minus 1 plus 2i times b equals to 0. So a is equal to 1 plus 2i times b, and now if you choose b to be 1, then a is 1 minus 2i. Much better. So this is v1. Yep. Well, constant multiples of it. But the, I want to say ratio between the correspondence between them has to be the same. Okay, v2. We have 1 plus 2i, and then minus 5, and then 1, and then negative 1 plus 2i times ab is equal to 0, 0. What happened? I wrote something.
Waking
It's
up.
supposed to be plus 2i.
They're waking up.
Oh, yes.
Hey, that's neat. What? It is supposed to be 1 plus 2i.
What he said.
Yeah.
I was comparing.
So now we have a plus, I'm going to factor the minus. Watch my minus signs. And b equals to 0. A is equal to 1 minus 2i times b. And then we, yeah, that's good. So now if I choose b to be 1, my a is 1 minus 2i. So to compile solutions, we actually don't have e's to deal with like we had before, right? We don't have this part, but we have everything else. So we are going to, yeah, it's a cosine of 2t. So for the first one, we have the C1 times the eigenvector, which is 1 plus 2i and then 1, times the cosine 2t minus I sine 2t. I don't even need C1. C1 I'm going to put actually in the end. So when I multiply this, it's going to be trickier because we have 1 plus 2i, right? So you go first 1 times everything. So that's cosine 2t minus I sine 2t. And then times this by, and then I, right? So plus 2i cosine t. And then minus, so plus 2i sine 2t. It's negative 2i squared. If it's negative 2i squared, I squared is negative 1, negative 2 times negative 1 is positive 2. Oh, yeah. Yeah, you can tell that I'm done, right? And then cosine 2t minus I sine 2t. Yeah, that's x1. Now we go x2. Of t. How's your carpet down? You did? It's painful, right? Not done yet? Cosine 2t minus I sine 2t minus 2i cosine 2t, and then 3 minus sine stays minus 2 sine 2t, and then the bottom is a cosine 2t minus I sine 2t, and then we're done there. So now for the solution, we keep the real parts when we have to remember to multiply by C1 and C2, and we also need to make sure that we are not including these because the real part of the eigenvalue is 0. So C1 times the matrix, we have a cosine 2t plus 2 sine 2t. So cosine 2t plus 2 sine 2t. And then cosine 2t here. And then plus C2 of, keep the real parts, so cosine 2t minus 2 sine 2t divided by the cosine 2t. Now if you see there is a cosine 2t in all of these, so you can make this a little bit better by kicking out cosine 2t and then having C1 1 plus 2 sine 2t and then 1 plus C2 1 minus 2 sine 2t and then 1. And I guess this is the cue because people are packing that I should stop talking, but I won't. And this is a 1, not a 3 or something like that. There we go, number 1.
How do you pull the cosine 2t with the sine?
Like this. I'm not gonna make the tangent. I was planning on making a tangent, then I forgot, and I'm not gonna do it now. I am not fixing it. There we go. Perfect. All right. So, do you expect these problems on the final? The answer is yes. The eigenvalue problem is almost guaranteed. So is the Laplace. So is the constant coefficients with either undetermined or the variation. So is the separation of variables. These things must be on the final, guys. So this, the problems that we did tonight, out of 4 examples that we did, one of these problems must show up on a final in one of its forms.
It's not actually going to show up as the